Okay. Hi everyone. Today we are going to discuss about MOED, molecular orbital energy level diagram. So MOED of H2 molecule, molecular orbital energy level diagram of H2 molecule. Second one, MOED, molecular orbital energy level diagram of N2 molecule. Next, MOED, molecular orbital energy level diagram of O2 molecule. Next, MOED, molecular orbital energy level diagram of O2 plus 1. O2 plus 1. So MOED of H2, MOED of N2, MOED of O2, MOED of O2 plus 1 are already completed in previous classes. So next heading, MOED of O2 minus 1. MOED of O2 minus 1. Molecular orbital energy level diagram of O2 minus 1. Important. MOED of O2 minus 1. O2 minus 1. Molecular orbital energy level diagram of O2 minus 1. So MOED of H2, MOED of N2, MOED of O2, MOED of O2 plus 1 are completed in previous classes. And next heading, MOED of O2 minus 1. O2 minus 1. First of all, O2 minus 1. O2 minus 1. So O2 minus 1 converted into O plus O and negative charge minus 1. Minus 1. Clear. So first oxygen atom. Next O minus 1. O minus 1. Clear. Generally oxygen atomic number 8. Oxygen atomic number 8. And O minus 1 means gaining of 1 electron. For example, O plus 1 loss of 1 electron. O minus 1 gaining of 1 electron. So it is O minus 1. So O minus 1 means gaining of 1 electron. In oxygen, total electrons are 8 and minus 1 gaining of 1 electron. So total electrons are 9. Okay? So oxygen atomic number 8. Next O minus 1, total electrons are 9. And electron configuration is 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. Next same O minus 1, electron configuration is 1s2, 2s2, 2p5. 2p5. So 1s2, 2s2, 2p4. Total electrons are 8. 2 plus 2, 4. 4 plus 4, 8. Next O minus 1, total electrons are 9. So 1s2, 2s2, 2p5. 2 plus 2, 4. 4 plus 5, 9 electrons. 9 electrons. Okay. So very simple. S orbitals always 1. Same S orbital always 1. And P orbitals are 3. Px, Py, next Pz. Px, Py, Pz. Next O minus 1. Same 1s2, 2s2, 2p5. So 5 plus 2, 7. 7 plus 2, 9. 9 electrons. So S orbitals always 1. Same S orbitals always 1. And P orbitals are 3. That is Px, next to Py, next to Pz. Px, Py, Pz. Clear. And electron configuration 1s2, next to 2s2, next to 2p4. 1s2, 2s2, 2p4. Next electron configuration 1s2, next to 2s2, 2p5. 2p5. 1s2, 2s2, 2p5. So 1s2, 2 electrons. 2s2, 2 electrons. 2p4, 1, 2, 3, 4. Clear. Next 1s2, 2 electrons. 2s2, 2 electrons. 2p5, 1, 2, 3, 4, 5. And these are atomic orbitals. These are atomic orbitals. And atomic orbitals combine and to form molecular orbitals. So 1 plus 1, atomic orbitals combine and to form molecular orbitals. So first one is bonding molecular orbital. And second one, anti-bonding molecular orbital. Bonding molecular orbital, next one anti-bonding molecular orbital. Same atomic orbitals combine and to form molecular orbitals. First one bonding molecular orbital and second one anti-bonding molecular orbital. Bonding, next anti-bonding. Next 3 plus 3, 6. So 1, 2, 3, 4, 5, 6. So these 3 are bonding molecular orbitals and remaining 3 are anti-bonding molecular orbitals. Bonding molecular orbitals, anti-bonding molecular orbitals. Okay. So bonding molecular orbital. C is bonding molecular orbital. Next one anti-bonding molecular orbital. Same bonding molecular orbital. Same anti-bonding molecular orbital. So these are atomic orbitals and remaining middle one is molecular orbitals. Molecular orbitals. So 2 plus 2, 4 electrons. 1, 2, 3, 4. 2 plus 2, 4 electrons. 1, 2, 3, 4. Clear. Next 4 electrons plus 5 electrons. 9 electrons. Total 9 electrons. So filling of electrons very simple. 1, 2, 3, 4, 5, 6, 7, 8, 9. So total electrons are 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7, 8, 9. So it says sigma 1s2, sigma 1s2, and it says sigma star 1s2, sigma star 1s2. Antibonding symbol star 1. Next it says sigma 2s2, and next one sigma star 2s2, sigma star 2s2. And individual orbital is pz, that is sigma 2p z square 2 electrons. Next pi 2p x square. Next pi 2p y square. Okay, so sigma 2p z square 2 electrons, pi 2p x square 2 electrons, pi 2p y square 2 electrons, and these 3 are bonding molecular orbitals. Bonding molecular orbitals. And next one says sigma star antibonding symbol 2p z 0. There is no electrons. There is no electrons. And next pi star 2p x square, 2p x square. Next pi star 2p y 1, only 1 electron, so 1. And sigma star 2p z 0, there is no electrons. Next pi star 2p x square, 2 electrons, 2 electrons. So these are molecular orbitals. Molecular orbitals. First one is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Next one individual orbital pz, sigma 2pz square, pi 2p square, and pi 2py square. And these two are degenerate orbitals, are equal energy level orbitals. Next one sigma star 2pz 0. Next pi star 2px square 2 electrons, pi star 2py1 only 1 electron. So it says MOED or molecular orbital energy level diagram of O2 minus 1 ion. O2 minus 1 ion. Okay. First point is bond order. Bond order. First point, bond order. Bond order. So generally bond order principle of into bonding molecular orbital electrons minus anti-bonding molecular orbital electrons. So generally bond order principle of into bonding molecular orbital electrons minus anti-bonding molecular orbital electrons. So of into bonding molecular orbital electrons are, so bonding molecular orbital and bonding molecular orbitals. So 2 electrons plus 2 electrons 4 plus 6 electrons 10. So bonding molecular orbital electrons are 10 minus anti-bonding molecular orbital electrons. So anti-bonding molecular orbitals, same anti-bonding molecular orbital, same anti-bonding molecular orbitals. So 2 electrons plus 2, 4 electrons plus 3, 7 electrons. So anti-bonding molecular orbital electrons are 7, 10 minus 7. So half into 3, that means 3 by 2. So bond order is 1.5. Okay. So bond order of nitrogen molecule 3. Bond order of oxygen molecule 2. Bond order of O2 plus 1 2.5 and bond order of O2 minus 1 1.5. Okay, so half into bonding molecular orbital electrons minus anti-bonding molecular orbital electrons. So half into bonding molecular orbital electrons are 10 minus anti-bonding molecular orbital electrons are 7. So half into 3. So bond order is 1.5. And second point, magnetic property. Second point is magnetic property. Magnetic property, para or di. So magnetic property. So for example, only unpaired electron, presence of one unpaired electron, So unpaired electron, paramagnetic property, and complete paired electron, so diamagnetic property. So only one unpaired electron, presence of unpaired electron, so magnetic property is paramagnetic property. And third one, energy level of O2 minus 1 ion. Energy level of O2 minus 1 ion. So first sigma 1s2, and next one sigma star 1s2, next sigma 2s2, next sigma star 2s2, next sigma 2pz square, 2 electrons, and next pi 2px square is equal to pi 2py square, and these two are degenerate orbitals, are equal energy level orbitals. So sigma 2pz square, next pi 2px square is equal to pi 2py square, next pi star 2px square, next pi star 2px square is equal to pi star 2py1, next sigma star 2pz0. So this is energy level of O2 minus 1 ion. Okay, so sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, next sigma 2pz square, and pi 2px square is equal to pi 2px square, is equal to pi 2py square, next pi star 2px square, is equal to pi star 2py1, next sigma star 2pz0. So finally, first point is bond order. So bond order is called half into bonding molecular orbital electrons minus antibonding electrons. So half into 10 minus 7, so half into 3, so bond order is 1.5. And second one, magnetic property, paramagnetic property due to presence of an unpaired electron. And next one, energy level of O2 minus 1 ion. So this is MOED of O2 minus 1. So first one, MOED of H2, MOED of N2, MOED of O2, MOED of O2 plus 1, MOED of O2 minus 1. And next, next one, MOED of helium-2 molecule, He2. First of all, helium-2 molecule. Okay, so helium-2 molecule. So helium, next helium, clear. Generally helium atomic number 2, same helium atomic number 2. So electron configuration 1s2, same electron configuration 1s2, clear. So s orbital only 1, clear. Electron configuration 1s2. Electron configuration 1s2. Next to 2 electrons. Same 1s2, 2 electrons. Okay. So helium. Next helium. Helium atomic number 2. Next helium atomic number 2. Electron configuration 1s2. Electron configuration 1s2. S orbital only 1. S orbital only 1. 1s2, 1s2. 2 electrons, and these are atomic orbitals. Atomic orbitals combine and to form molecular orbitals. First molecular orbital, second molecular orbital. So first one is bonding molecular orbital. Second one anti-bonding molecular orbital. Clear? 2 plus 2, 4 electrons. 1, 2, 3, 4. So first one sigma 1s2, sigma star 1s2. Clear? So bond order principle. Bond order is equal half into bonding molecular orbital electrons minus anti-bonding molecular orbital electrons. Okay. So half into bonding electrons are 2 minus anti-bonding electron, same anti-bonding electrons also 2. So half into 2 minus 2, 0. 2 minus 2, 0. So bond order is equal 0. So in helium 2 molecule, bond order is equal 0. So helium 2 molecule does not exist. So in helium 2 molecule bond order is 0. So helium 2 molecule does not exist. So finally helium 2 molecule does not exist because helium 2 molecule bond order is 0. Okay, so helium 2 molecule does not exist. So helium 2 molecule bond order is 0. So if bond order is equal 0, the molecule does not exist. If bond order is equal 0, the molecule does not exist. And next one, very very important. For example, helium 2 plus 1. Important of helium 2 plus 1. So first of all, helium. Next to helium, clear. Helium 2, clear. Helium. Next to plus 1 charge, plus 1. Okay. So helium atomic number 2. Next helium actual atomic number 2. Plus 1 means loss of 1 electron. And remaining electrons are only 1. So helium 2 plus 1. So helium. Next plus 1. Actual helium atomic number 2. Same helium atomic number 2. But plus 1 means loss of 1 electron. Remaining electrons are only 1. And electron configuration 1s2. Next electron configuration 1s1. So s orbital only 1. Same s orbital only 1. So 1s2. Next 1s1. 1s2 2 electrons. Next 1s1 only 1. And these are atomic orbitals. Atomic orbitals combined and to form molecular orbitals. So very simple. First molecular orbital. Next one, second molecular orbital. So first one is bonding molecular orbital, and second one anti-bonding molecular orbital. Next one anti-bonding molecular orbital. So generally 2 plus 1 total electrons are 3. So 1, 2, 3. So this is sigma 1s2 and this is sigma star 1s1. Sigma 1s2, sigma star 1s2. So bond order. So bond order principle. Bond order is equal half into bond order principle. Half into bonding molecular orbital electrons minus anti-bonding molecular orbital electrons. So half into bonding molecular orbital electrons minus anti-bonding molecular orbital electrons. So half into bonding electrons. Bonding electrons are 2 minus anti-bonding electrons 1. So half into 1, that means 1 by 2. 1 by 2 means bond order is 0.5. In helium 2 molecule bond order is 0. But in helium 2 plus 1, bond order is 0.5. So helium 2 molecule does not exist, but helium 2 plus 1 molecule is exist. Okay, so if bond order is equal 0, if bond order is equal 0, the molecule does not exist, does not exist. In helium 2 molecule, bond order is 0, so helium 2 molecule does not exist, does not exist. But in helium 2 plus 1, bond order is 0.5, so helium 2 plus 1 ion is exist. So helium 2 molecule does not exist, but helium 2 plus 1 ion is exist. Because in helium 2 molecule bond order is equal to 0, but in helium 2 plus 1 ion bond order is 0.5. So helium 2 molecule does not exist and helium 2 plus 1 molecule is exist. So says does not exist and exist molecule helium 2 plus 1. Helium 2 plus 1. So says MOED, molecular orbital energy level diagram. So topic close. Okay. So MOED of H2, MOED of N2, MOED of O2, MOED of O2 plus 1, MOED of O2 minus 1. Next MOED of helium 2, MOED of helium 2 plus 1. So helium 2 molecule does not exist because bond order is 0. But helium 2 plus 1 molecule is exist because bond order is 0.5. So if bond order is equal to 0, if bond order is equal to 0, the molecule does not exist. The molecule does not exist. So helium 2 molecule does not exist compared to helium 2 plus 1. 2 plus 1. So this is MOED, molecular orbital energy level diagram. Close. Okay. And next topic. So MOED close. Molecular orbital energy level diagram. Next topic. Next topic, very important, hybridization. So MOED close, MOED of H2, MOED of N2, MOED of O2, MOED of O2 plus 1, MOED of O2 minus 1, and MOED of helium 2 plus 1 and helium 2. Helium 2 molecule does not exist because bond order is equal to 0. Next, very important topic, previous 8 marks question is hybridization. Okay, so what is meant by hybridization? Very simple. The intermixing of atomic orbitals. Of almost equal energy. The intermixing of atomic orbitals of almost equal energy, and their distribution, an equal number of new type of hybrid orbitals. Is called hybridization. So what is meant by hybridization? Very simple. The intermixing of atomic orbitals of almost equal energy, and their distribution, an equal number of new type of hybrid orbitals is called hybridization. So the intermixing of atomic orbitals of almost equal energy, and their distribution into an equal number of new type of hybrid orbitals is called hybridization. For example, the intermixing of atomic orbitals of almost equal energy and their distribution into an equal number of new type of orbitals is called hybridization. So finally hybridization means the intermixing of atomic orbitals. The intermixing of atomic orbitals of almost equal energy and their distribution an equal number of new type of hybrid orbitals is called hybridization. It's called hybridization. So first of all, subheading very important, that is SpHybridization. First one subheading, that is SpHybridization. 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 Okay? SpHybridization. So best example of SpHybridization, that is beryllium chloride, BeCl. Best example of SpHybridization, that is beryllium chloride. Generally beryllium chloride formula BeCl2. So best example of hybridization, that is beryllium chloride. Beryllium chloride. So in beryllium chloride, central atom is beryllium. In beryllium chloride, central atom is beryllium. And beryllium atomic number 4. Beryllium atomic number 4. And electron configuration is 1s2, 2s2, 2p0. No problem. 2p0. 2p0. So total electrons are 4. 2 plus 2, 4 electrons. 1s2, 2s2, 2p0. And outermost electron configuration is 2s2, 2p0. Okay? S orbital only 1 and p orbitals are 3, px, py, pz. 2s2, 2 electrons, 2p0, there is no electrons. There is no electrons. Then first excitation state. Then 2s orbital electron enter into 2px1, 2px orbital. 2s orbital electron enter into 2px orbital, 2px orbital. Clear? So best example of SpHybridization, that is beryllium chloride. In beryllium chloride, central atom is beryllium and beryllium atomic number 4. And electron configuration is 1s2, 2s2, 2p0. And outermost electron configuration 2s2, 2p0. S orbital only 1 and p orbitals are 3, px, py, pz. 2s2, 2 electrons, 2p0, there is no electrons. Then first excitation state, 2s orbital electron enter into 2px orbital. So 2s1, 2px1. 1 s orbital and 1 p orbital. 1 s orbital, 1 p orbital. So sp, 1 s orbital, 1 p orbital. And total orbitals are 2. So 2 moles of sp hybrid orbitals. Sp hybrid orbitals. So finally SpHybridization means the intermixing of 1 s orbital. The intermixing of 1 s orbital. And 1 p orbital. The intermixing of 1 s orbital and 1 p orbital of outermost shell of an atom is called SpHybridization. The intermixing of 1 s orbital and 1 p orbital. The intermixing of 1 s orbital and 1 p orbital of outermost shell of an atom is called SpHybridization. SpHybridization. So finally SpHybridization means the intermixing of 1 s orbital and 1 p orbital of outermost shell of an atom is called SpHybridization. SpHybridization. Clear? So beryllium atomic number 4, electron configuration 1s2, 2s2, 2p0, outermost 2s2, 2p0. So s orbital 1 and p orbitals are 3. 2 electrons, p0, there is no electrons. Then first excitation state, 2s orbital electron enter into 2px orbital. So 1 s orbital, 1 p orbitals and total orbitals are 2. So 2 moles of 2 sp hybrid orbitals. The intermixing of 1 s orbital and 1 p orbitals of outermost shell of an atom is called SpHybridization. Clear? So beryllium close. Next chlorine atom. Generally chlorine atomic number. Chlorine atomic number 17. Chlorine atomic number 17. And electron configuration of chlorine atom, that is 1s2, 2s2, 2p6, 3s2, 3p5. And outermost electron configuration is 3s2, 3p5. 3s2, 3p5. So very simple, 1 s orbital, 1 s orbital. And p orbitals are 3, px, py, pz. 3s2, 2 electrons. And 3p5, 1, 2, 3, 4, 5. Clear? Every chlorine has a 1 unpaired electron. That means single electron. So total chlorine atoms are 2. Every chlorine has a 1 unpaired electron. and total chlorine atoms are 2. So total unpaired electrons are 2. Okay, first of all central atom beryllium, okay, and 2 sp hybrid orbitals, 2 sp hybrid orbitals, first mole sp hybrid orbital and second one sp hybrid orbitals. Next, every chlorine has a one unpaired electrons, that is pz orbital. So pz orbital of chlorine atom, pz orbital of chlorine atom, first chlorine atom. Next, pz orbital of second chlorine atom, pz orbital of first chlorine atom. Next, pz orbital of second chlorine atom. So every chlorine has a one unpaired electron. So pz orbital of first chlorine atom, pz orbital of second chlorine atom. So this is central atom, that is beryllium. Next, chlorine atom Cl. Next, chlorine atom Cl, BeCl2, BeCl2, beryllium chloride, beryllium chloride. And this is sigma sp pz hybrid orbital. So sp hybrid orbital and pz orbital of chlorine atom. So sigma sp pz bond. Next one, same, sigma sp pz bond. So this is orbital structure of beryllium chloride. So finally, shape of the beryllium chloride molecule, that is linear, straight line. So linear shape. And bond angle in beryllium chloride, that is 180 degrees. So shape of the molecule linear and bond angle is 180 degrees. And final structure of beryllium chloride. So central atom beryllium and remaining two chlorine atoms, first chlorine atom, second chlorine atom, and bond angle is 180 degrees. So this is sp hybridization. Okay, so first of all, what is meant by sp hybridization? The intermixing of one s orbital and one p orbital of outermost shell of an atom is called sp hybridization. And best example of sp hybridization, beryllium chloride, and central atom beryllium, atomic number 4, 1s2, 2s2, 2p0. So outermost 2s2, 2p0, s orbital 1, p orbitals are 3, and first excitation state 2s orbital electron enter into 2px orbital. So 1s orbital, 1p orbital. So total 2 moles of sp hybrid orbitals. Next, chlorine atomic number 17, 1s2, 2s2, 2p6, 3s2, 3p5. Every chlorine has a one unpaired electron. Okay. First of all, beryllium, 2 sp hybrid orbitals, and every chlorine has a one unpaired electrons. So pz orbital of chlorine atom or pz orbital of first chlorine atom. Next, pz orbital of second chlorine atom. And this is sigma sp sp hybrid orbital. Next, pz. So sigma sp pz bond. Second one, same, sigma sp hybrid orbital and pz orbital of chlorine atom. So sigma sp pz bond. And structure of beryllium chloride linear, and bond angle of beryllium chloride 180 degrees, and final structure beryllium chloride BeCl2 and bond angle is 180 degrees. So this is sp hybridization. So hybridization means the intermixing of atomic orbitals of almost equal energy and their distribution into an equal number of new type of hybrid orbitals is called hybridization. And first one is sp hybridization, and best example of sp hybridization, beryllium chloride. Next,
33.
sir,
33.
so best example of sp hybridization, that is beryllium chloride. So first one sp hybridization. Next, second one very simple, sp2 hybridization. So first one sp hybridization and second one sp2 hybridization. Very simple, sp2 hybridization. And best example of sp2 hybridization, that is boron trichloride, formula BCl3. Formula BCl3. So in boron trichloride, central atom is boron. Atomic number is 5. So best example of sp2 hybridization, that is boron trichloride BCl3, and central atom is boron, atomic number 5. So electron configuration of boron 1s2, 2s2, 2p1, 2p1. So total electrons are 5, 1s2, 2s2, 2p1. And outermost electron configuration is 2s2, 2p1, 2s2, 2p1. Okay. So s orbital only 1 and p orbitals are 3, px, py, pz. 2s2, 2 electrons, 2p1, only 1 electron, only 1 electron. Then first excitation state. 2s orbital electron enter into 2p y orbital. 2s orbital electron enter into 2p y orbital. So 2p x1, 2p y1, 2p y1. Okay. So boron atomic number 5. Electron configuration 1s2, 2s2, 2p1. Outermost electron configuration is 2s2, 2p1. So 2s2, 2p1. Next first excitation state. 2s orbital electron enter into 2p y orbital. So the intermixing of one s orbital and 2 p orbitals. The intermixing of one s orbital and 2 p orbitals. So 1 plus 2, 3. 1 s orbital, 2 p orbitals, 2 p orbitals. So 3 moles of sp2 hybrid orbitals. sp2 hybrid orbitals. The intermixing of one s orbital and 2 orbitals. So total orbitals are 3. So 3. S orbital, 1 s orbital. 2 p orbitals, 2 p orbitals. So 3 moles of sp2 hybrid orbitals. sp2 hybrid orbitals. So finally sp2 hybridization means the intermixing of one s orbital and 2 p orbitals of outermost shell of an atom is called sp2 hybridization. Simple definition. The intermixing of an s orbital, 2 p orbitals of outermost shell of an atom is called sp2 hybridization. So boron atom close. And next one, chlorine. Generally chlorine atomic number 17. Chlorine atomic number is 17. And electron configuration 1s2, 2s2, 2p6, 3s2, 3p5. Total electrons are 17. 1s2, 2s2, 2p6, 3s2, 3p5. And outermost electron configuration is 3s2, 3p5. S orbital only 1 and p orbitals are 3, px, py, pz. So 3s2, 2 electrons. Next to 3p5, 1, 2, 3, 4, 5. And every chlorine has a 1 unpaired electron. And total chlorine atoms are 3. So total unpaired electrons 3. So every chlorine has a 1 unpaired electron and total chlorine atoms are 3 and total unpaired electrons are 3. Okay. So first of all central atom boron. And boron has a 3 sp2 hybrid orbitals. 3 sp2 hybrid orbitals. First sp2 hybrid orbital. Total number 3 sp2 hybrid orbitals. First sp2 hybrid orbital. Second one, next third one. Next every chlorine has a 1 unpaired electrons. So total chlorine atoms are 3. So first chlorine pz orbital. Clear. Next second chlorine pz orbital. Next third chlorine pz orbital. Okay. So first of all boron 3 sp2 hybrid orbitals. First one, second one, third one. Next every chlorine has a 1 unpaired electron. So first chlorine pz orbital, next second chlorine pz orbital, next third chlorine pz orbital. So this is boron atom. Next chlorine Cl, next chlorine Cl, next chlorine Cl, BCl3. And this is sigma sp2 pz bond. Sigma sp2 pz bond. Same says sigma sp2 pz bond. Sigma sp2 pz bond. Same says sigma sp2 pz bond. So sp2 hybrid orbital and pz hybrid orbital. sp2 hybrid orbital and pz. sp2 and pz. So sigma sp2 pz, sigma sp2 pz, sigma sp2 pz. And shape of the molecule Shape of the molecule, that is trigonal planar, and shape of the molecule is trigonal planar, and bond angle is 120 degrees. 120 degrees. So in beryllium chloride, shape of the molecule linear and bond angle is 180 degrees. In boron trichloride, shape of the molecule trigonal planar and bond angle is 120 degrees. 120 degrees. And final structure of BCl3. Final structure of BCl3. So central atom is boron. Next 3 chlorine atoms. First chlorine atom. Next second chlorine atom. Next third chlorine atom. And bond angle is 120 degrees. 120 degrees. So this is sp2 hybridization. So finally sp2 hybridization means the intermixing of one s orbital and 2 p orbitals of outermost shell of an atom is called sp2 hybridization. And best example of sp2 hybridization is boron trichloride. Boron trichloride. Okay, so boron atom. Next chlorine atom. Every chlorine has a one unpaired electron. Okay, so boron atom 3 sp2 hybrid orbitals. So pz orbital of first chlorine atom, pz orbital of second chlorine atom, pz orbital of third chlorine atom. So BCl3. And shape of the molecule trigonal planar, and bond angle is 120 degrees. Bond angle is 120 degrees. And final structure of BCl3 trigonal planar. So this is sp2 hybridization. So what is meant by what is meant by hybridization, and types of hybridization, sp and sp2. Okay, sp hybridization. Next one, sp2 hybridization. Close. Okay.